Hello, a bit of a cheeky video this week because if you've been following my videos, you're probably quite familiar already with the OLC console game engine. However, I've had some comments and some private messages from viewers that have requested that I give them a little bit more of a helping hand with it. They know a little bit of C++ or C, and they want to have a little fun with it, and the OLC console game engine has shown that you can get things up and running that are quite fun, quite simply. So up front, this video is not for everybody, but I'd like to have it on the site as a visual reference guide for people who want to have a go themselves. And when I mean start from the beginning, I mean really start from the beginning. So I use Microsoft's Visual Studio 2015. This is the Community Edition, and it's free to download, and it's fully featured. And certainly all of my code, if it can be compiled in this version, it can be compiled in 2017, which is the most recent version. Now the first thing we're going to need to do is create a console game engine project. So we go to File, New, Project. You can see I've got a list of predefined things that I like to play with, but what we want is the most simple one, the Win32 console application. Let's give it a name. I'll call it Example Project. And you can see it'll create the folder for us as well. Click the OK button to continue, and then we go back to a menu here. Now this menu has been around for a long time. I think I remember seeing this first in Visual Studio 5 maybe? Definitely it was in 6. Anyway, we want a console application, so we click the Next button. I want to make sure that we've got console application as the radio button that's checked, and I like to get rid of a few things. So definitely I want to get rid of precompiled header, and I want to create an empty project. We're not adding any files or getting Windows to generate any code for us. And then we can click Finish. So now we've got an empty project in Visual Studio. And I can't zoom in on these, so take my word for it, but if you right click on the example project in the projects window, we can go to Add, New Item, and we want to add a new C++ file. I'll stick with the source.cpp as the file name. And click Add. Now there'll be no code to start with, so we want to add that ourselves. The first thing I'm going to include is IOStream. And as that's part of the standard library, I want to include the standard namespace. It's just an int main, that's all we need. Now some of you may think, well, what if I want to pass arguments into here? Well, you can do that as well, but I don't tend to bother. We'll have an int main, and by default we'll return 0. At the moment our project only consists of the source.cpp file. If we want to use the console game engine file that you've seen in my videos, we'll need to download it. The easiest way to get hold of the source code is to go to my YouTube channel, which is youtube.com/javidx9. And from here, if we look at the little shortcut icons, we can see the furthest to the right is for GitHub, which is a place where I store all of the code. In fact, I have 3 repositories here, and the one we're interested in is videos. If you're familiar with GitHub, you can clone it as you see fit. I'm just going to download the whole lot as a zip file. Once the download is finished, we can open up the zip file and take the file that we need. In this case, olcConsoleGameEngine.h. And then I'm going to navigate to the project folder we created earlier, and we can see this is the solution folder, example project. The actual project is another folder within that, example project, and we can see our source CPP file. So I'm going to paste the olcConsoleGameEngine.h file into that folder. And we can go back to Visual Studio, right click on example project, add existing item, and we'll just add the source. And we can see that it's become part of the project. And here it is. I'll zoom out a little bit. The most recent version of the console game engine file. When we're using the console game engine, we mustn't forget that it is in fact a command line program. It is a command prompt program. There are no graphics involved, and everything that we see is generated using text. And because we know all of the characters of the text occupy the same amount of area, we can treat them as pixels. So here is a drawing of the console set up as a 2D array. And typically we would have 0, 0 for x and y in the top corner. And in the console game engine, we find the width as screen width. It's a function that will return it. And we can find the height as screen height. It's important to know about this layout because really there isn't a 2D array here, there's a 1D array. And so the first element will be 0, 1, 2, 3, 4, 5, 6. And so in this system we've got 7 columns. So our screen width would be 7. But these are memory addresses to locations on the screen. And once we get to the end of a row, it wraps back round to here again. 7, 8, 9, 10. And so forth. Now we'll see later on that whenever we use a command to draw something to the screen, we specify an x and a y coordinate. Or we can resolve this 2D system to a 1D system to suit our array with the simple calculation y times screen width plus x. And we can check that out. So let's say I want to get to this location here, which is column 3 and row 1. If we throw that in, we get 1 times 7, which is our number of columns across the screen, plus 3 equals 10. Now, because this is a console, each one of these locations represents a character, not a pixel. And so the screen is actually made up of an array of char info structs. And we'll look at the detail of those in a minute, but essentially these break down into the glyph and the palette. And the glyph is what the character looks like, so a letter A, for example, or an ampersand. And the palette is split into two, one that represents the foreground colour and one that represents the background. Many new programmers will be familiar with the glyphs being represented as ASCII, which is an 8-bit encoding for character information. In fact, it's traditionally a 7-bit encoding, but they wanted some extended characters, such as angle brackets and filled-in squares. And so they added the extra bit to create extended ASCII. And so in C++, it is most common to use the type char, or car, depending on where you're from. But this is a little bit old-fashioned now, and doesn't accommodate many symbols, and it's not that compatible with other languages other than, say, the Western alphabet. So instead, the console game engine by default is set up to use Unicode, which in this case is a 16-bit implementation. And this, of course, gives us 65,356, if I remember my math correctly, different code points for the Unicode. So that many different possibilities of character are available to us. So to represent this data, we could, of course, use an unsigned short. But there's a more accepted analogous type called a wchar, standing for wide character T. And in some Windows applications, you may even see tchar, which I believe at compile time is determined to be either a char or a wchar, depending on your compiler settings. But by default, the game engine uses this. Let's use a flow diagram to analyse how the game engine works. The first thing the user will do is construct the console, and to this they will specify how many characters wide, by how many characters high it should be, and how big those characters should be on the screen, whether they're 8 pixels by 8 pixels, or 12 pixels by 12 pixels, or any measurement you like, really. If it is possible to create such a console, this function will return true. There are situations where it isn't possible to create such a console. They may not fit on a single screen, for example, if you've specified your characters to be too large, in which case the whole game engine will just say, cannot do it, and exit to the command line again. However, if it does return true, the user can then call the start function. And the start function will start a behind-the-scenes thread which will run the game engine. And the first thing this thread will do is call create and load resources, or you'll see this as on user create. Which is a function you can override to create the resources that you need for your game. And it's important that the thread owns these resources, because some resources can be a bit sensitive to who owns them. So here you might want to load level data, map data, sprite information, sound information, all of the things that are going to exist within your game world, the sort of the static data, the stuff that doesn't change. You can also use this function as an initializer function for other variables and game states. If you can't load a resource for whatever reason, you must tell this function to return false, at which point it'll exit the application. So now there's a thread running in the background, you've loaded all your resources, we then enter the game loop. And the first thing the game loop will do is update all of the timing information it needs to operate properly. This part of the code will give us our elapsed time variable. And this is the recorded time, i.e. the length of the previous frame. Now you might be thinking, well, surely the length of a frame is fixed in time. And indeed, we want to give that perception. But consider the scenario. Let's say I've got a game where I've got a ball moving around on the screen. we know that updating the position of the ball takes 5 instructions, and so every loop we've got a 5 instructions worth of game. So in many respects you could think, well, it's always going to take the same amount of time, but as soon as I add another ball, I've now got 10 instructions, and what if this ball goes off the screen and no longer needs to be processed? So the amount of processing, the load on the system, changes per frame. But it gets even worse. Our game is competing for resources from the operating system, so there are other things running, such as OBS, YouTube, virus scanners, etc, etc, etc. You've got loads of things on your computer all competing for processing time, of which there is only a certain amount. And so it turns out that the elapsed time of a frame can be quite variable indeed. But so what, I hear you say? Well, it's actually quite important to use this elapsed time in our processing to give the appearance of smooth motion. Let's take our ball as an example. Let's say we want the ball to move smoothly across the screen. We know that the distance it travels is equal to the speed we want it to move at times time. If we have time fixed as a constant, the simulation will be accurate. But the user experience will be awful, and that's because the CPU load varies. As the CPU load goes up, we can only update our game less frequently. So that will give the impression of the ball slowing down, because we're not calling our game loop as many times. And as the CPU load decreases, then we start to update more. And in this case, the ball will speed up. And on the whole, this will be a very unsatisfying user experience. So what's important to do is to modulate our constant t with f-elapsed time. And f-elapsed time works on wall time, so this brings some reality into our simulation. The elapsed time variable comes through as seconds, and in most cases it'll be 0.000 something or other. And if we use the equation f equals 1 over time, we can see that if our f-elapsed time is something like this, then our frames per second, which is the frequency, the update, is very high. In fact, in this case, it'll be 10,000 FPS, which means we get a lot of updates to the dynamics of our ball. We get 10,000 of them a second. And if we're telling the ball to move at, say, 5 meters per second, to give the appearance of it moving at 5 meters per second, we need to divide up that 5 by the number of updates that we're calculating. So we can use f-elapsed time to subtly change the behavior of objects so it looks like a consistent movement for the user. And this is really, really, really important. Once the game engine has approximated the time per frame, it then goes and updates the input. And this is where it reads from the mouse and keyboard and populates some structures to tell you whether for that frame has the mouse button or keyboard been pressed, has it been released, or is it held down. And so in the example of the keyboard, this fills an array called m_keys, and you can use the virtual key codes in Windows to access these. So for arrow keys, for example, it's VK up. And we get a choice of B released, it's a boolean, has it been released, has it been pressed, or is it held down, i.e. was it held down or pressed on the previous frame. It's exactly the same for mouse, and this gives us the ability to emulate events. Once we've updated the state of the input, we then call the onUserUpdate function. And this is primarily to do two things, but we often combine them in ways just for convenience. So I'll draw a dashed box for this. So this box is onUserUpdate, and of course you get the f-elapsed time variable as part of this function call. And in here you do two things. The first is update the game state, and the second is everybody's favourite bit, update the screen. I.e. we draw any information we want to the screen. And they call this the game loop because if this function returns true, it goes right back round to here again. But if it returns false, it terminates the application. Let's go back to our source file now and include the game engine. The game engine class is abstract. it's deliberately intended that the programmer has to fill in some missing parts. In this case, it's the onUserCreate and the onUserUpdate functions. So we'll need to create a class that inherits from this abstract class. Now this may all sound a bit too much object-oriented programming, but it's actually quite a simple concept. So we'll declare our new class, we'll call it example, and we're going to tell it to publicly inherit from olcConsoleGameEngine. First thing we'll do is add a constructor. For now, it doesn't need to do anything. The second thing we'll do is override our onUserCreate function. To override it, we'll just keep a note to ourselves that it's virtual. We know it returns a boolean because if it returns false, it's going to exit the application. And it's exactly the same name, so it's onUserCreate. And it doesn't take any arguments. And by default we'll have it return true. We don't want it to exit. We should do something similar for our onUserUpdate function. So again, if that returns false, it's going to exit the application. onUserUpdate. And this will always include the parameter f_elapsed time. And it has an f at the front of it just to keep me informed that it's a floating point variable. And again, we'll have that return true. Using our class is quite simple. Example, demo. Once we've got the object, we want to create the console, and that's just calling the ConstructConsole function. And as I'm sure you're well aware from all of the other videos, we specify the width in characters, the height, and the individual sizes, width and height for the characters themselves. Then we simply call demo.start, which starts the thread in the background. So let's have a look at the source for the game engine. I'm going to start by looking at the private variables. We can see we've got 2 pointers to arrays that are going to store the keyboard state. Now these are going to be arrays because I'm going to store 256 different states. The arrays will be initialized in the constructor. And I'm also storing 2 Boolean arrays for the mouse buttons. I store 2 handles. Handle for hConsole, which by default is the output buffer, and hConsole for the input buffer. And it's this one which we use to handle mouse events. Keyboard events are a little bit different in this implementation. And I store some information which is used to return the console to its original state in the event of an error. Let's have a look at the constructor. So the constructor by default specifies a screen width of 80 and 30. That's a fairly small standard console. And I can see I get the handles to the standard input and standard output so I can communicate with the console. And I create my 2 arrays to store the keyboard. Now the keyboard will work by storing the old state and the new state and looking for differences between them per frame. And it's these differences we can use to trigger events that you'll use in your games. I default all of the keyboard states to 0. The construct console is really a bunch of calls to the Windows SDK. The first thing it will do is try to create a font of the required sizes, width and height of the individual characters. And this is necessary because in a couple of lines, we're going to call the getLargestConsoleWindowSize function. And this function will take the font size that we've just applied and tell me, by returning a coordinate structure, what is the largest possible console I can use that uses that font size. Once I know what is the largest possible console, I can check that against my own screen width and screen height. So if, for example, my screen height is larger than I'm allowed to have, it will return with an error. Game height is too big. If it passes both of these tests, that assumes that our parameters are valid. And then we can go on to create the screen buffer. The screen buffer represents the memory that sits behind the console. So I want to ensure that I've got enough rows and columns for characters. So I create a buffer with screen width and screen height as provided to this function, and I tell my console, this is the size you must use. Now in a little bit of a Windows quirk, that's not the same as setting the dimensions of the console window itself. So this function is just setting the size of the text buffer, and this function, setConsoleWindowInfo, is setting the size of the window. And we want them to line up. Now what I found mildly infuriating with this is these needs to be done in the right order. You've got to make sure that the memory is set up before you can adjust the window size, or it'll fail. Once we've created the console and everything is happy, we then create our screen buffer, which is the 2D array of char info structures. And if we take something as simple as our draw argument, we can see that the first thing it does is make sure that it is valid to draw it, that it's within the bounds of our screen, and if it is, we then write to that memory location using the equation I outlined earlier, y times the screen width plus x. And each char info structure, remember, consisted of the glyph, which in this case is the character that we want to display, and also some attributes, which happens to be the palette. Now the game engine conveniently has wrapped up the palette into a set of constants, and these are the foreground and these are the background colours. I've also created constants for some useful characters. So in this case, this is the Unicode equivalent, or the code point, for the solid block character. And you can have different shades of solid block character. It does it by dithering. Now let's have a look at the start function. Here we can see that we create a thread, and the start function will just block waiting for that thread to complete, and that's what this condition variable is doing. So the start function won't exit until we've allowed it to. And that's important, because in our int main, if this function returned immediately, the program would exit. This is the thread function, and the first thing it does is call onUserCreate. We then use the chrono library to access timing, so we can calculate our f-elapsed time. You don't need to use the chrono library, so if it's not available on your platform, you can change this to good old-fashioned C++ clock. And then once we've initialized the clocks and we've got the user's resources have been created, we then enter the game loop. That's just a simple while loop. So whilst everything is active, whilst it's allowed to run, we calculate the elapsed time, which is the current time minus the previous time. And we convert that to a float, so it makes all of our sums easier, and it gets rid of the really wordy chrono library from your applications. We then handle the input, like on the second stage of the flowchart. And these have been covered in their own videos. Once we've got the input, we then call onUserUpdate and pass along the f-elapsed time variable. If this function returns false, then we tell it that this thread should return false. The thread is no longer active, it's valid. We want it to end, so the next time it gets around to the while loop, it'll just simply not do it, and it'll pass through. Where it calls the condition variable and says, I've had enough, time to stop. There's a little bit of code here at the end, some more Windows SDK. If you've noticed in my applications, the title bar changes to show you the name of the application and the frame rate that you're running at, and then it does the most important call of all, write console output. And it is only because this function exists can we use the console as a game engine. In my command line first person shooter video, I showed how you couldn't use cout and the standard IO stream or printf methods to display information to the screen fast enough. This function basically allows us to swap our screen buffer to the console buffer in one hit. And so we write to our output console all of the memory that's in our screen buffer, and we can see how many bytes we want to send down. The start location, it's always going to be top left 00, and the size of the window we created earlier. And we can see we've got two pure virtual functions here. They're pure because they're specified equals 0. That means they must be implemented by the user. So if you try to compile this on its own, it won't let you. The compiler will say these are abstract, these are missing, you need to go and fill them in, what you're doing. Now I could start talking about all of the OLC sprite stuff and all of the drawing routines, but I think these have been covered in other videos, and I think it'll be more useful to show us creating a quick app just to prove everything we've done is legitimate. I don't need to do anything in my onUserCreate, because what I'm going to do is create an application that just simply shows a palette of all of the available colours on the screen. If we look at the colours available, we can see they're just incremental up until number 15. Before it changes to background. So I'm not going to use the constants, I'm just going to specify the number. To show the limited colour capabilities of the console game engine, I've created a little program which generates a swatch, like a grid of colours. So let's have a look. And we can see the main colours here, which are the ones specified by the palette in the console, are coarsely shaded using the different shaded characters. So I shade it with a dark character to give me a lower hue, and a whiter character to give me a lighter hue. It probably wouldn't take much effort to combine the dark hues with the vibrant hues of the same colour, and that way we could get a very nice function which could generate a colour for us, possibly derived from RGB, and perhaps then we could even display images and maybe even video. Maybe that's a subject for a future video. So this has been a quick look at the OneLoneCoder console game engine behind the scenes. I know we've done a similar video in the past. Due to some requests and a still growing number of subscribers, I felt it might be necessary just to have a little bit more of a background into how this technology works. Admittedly, it's not aimed at my mainstream audience, but I hope somebody finds it useful nonetheless. So please take the code, do whatever you want with it, hack it, have fun with it, and I'll see you next time.